All right, so you have some review material? You have a quiz coming up?
Yeah.
Or
What?
do you have a quiz coming up? Or
Yeah, I have a quiz tomorrow probably.
okay, over this material?
Yeah.
What do we got? Can you verbalize it?
Yeah. So use the properties of logs to rewrite each as a single logarithm.
Okay.
And the first one is 4 log xy minus 3 log yz.
YZ?
Yeah.
Okay. We have 3 main properties of logs. Do you want me to write them or do you know?
I think I need to go over them.
Okay, let's go over these are huge. The log of AB equals the log of A plus the log of B. Second one is basically the inverse of that. The log of A divided by B is subtracting. Log of A minus the log of B. And then for calculus, this is the most important one. The log of A to the B power equals B times the log of A. Okay?
Okay.
And you need to know these both ways. In other words, they're going to give you a series of problems that asks you to expand it, which is going in that direction. And then they're going to give you a series of problems that ask you to condense it, going in that direction. For example, this problem is asking you to condense. So, hold on 1 minute, or 1 second. Okay. So, we're going to have to use all 3 rules here.
All right.
Let's start out by using Rule 2. Now, hold on. Let me think here a second. It's probably better to start out by using Rule 3 in reverse.
All right.
Okay? So, how am I going to use Rule 3 and apply it to this?
So that would be, the first one would be log xy to the 4th.
Yeah, all in parentheses like this.
Yeah.
Okay? Minus what?
Minus log yz to the 3rd.
Okay? Now let's put these together using rule number 2.
Log xy to the 4th over y c to the 3rd.
Yeah, notice that all of these parentheses are necessary at this point. We're going to simplify this argument now. So, what does all that become?
Does that become...
Let's deal with one variable at a time. What do we have in the numerator in the way of x's?
4.
How about in the way of y's?
1.
And in the way of z's?
3.
In the denominator.
Yeah.
There's your answer.
All right.
Now, the only mistake that can be made when you do these is to omit the parentheses. And notice what happens if I forget to write them. Now it's just y being taken to the 4th.
Yeah.
not xy, and both of them need to be to the fourth. Now, one way to get around that is you can immediately distribute it like that if you don't want to use the parentheses. But I think the parentheses is actually useful for understanding what you're doing.
Yeah.
All right. Got another one?
Yeah, it's 1/3 log x. So would this be log cube root of x?
Yeah. Or we tend to use exponents a little bit more than radical signs.
Yeah.
Merely because they're so malleable. In other words, I can take that exponent and bring it down in front if I choose to. Now, this only works, these three rules, if you have the same base. In other words, in all of the cases you've given me, you've given me common logs, that's fine. But if I had the log base 2 of x plus the log base 3 of y, I can't do anything with that.
Yeah.
I cannot put them together. You can only put them together if it's the same base.
All right, the next one is log x.
Let me do this.
Plus,
Hold on a second. Let me do it this way. Okay?
plus log 5.
Log what?
Log 5.
Okay? What's that going to be?
So it would be log 5 plus x.
No? Go the other way. You're starting with this. Take it the other way.
Oh no, it would be log 5x.
Log of 5x. Is that what you said?
Yeah.
Uh-huh.
All right.
Now that is a number. Log of 5. So we actually could put a number in there and then solve for x. But you're not supposed to be solving for x, right? You're supposed to be reducing this expression or compressing it.
Yeah, into a single logarithm.
Right. Which is different than solving log equations.
Yeah.
Which we will get to. That's coming up.
All right, now the next part is use the change of base formula to rewrite using only natural log.
Okay.
And it's log 2
Here,
of 7.
Okay. The log of a base b is equal to the log of the higher number divided by the log of the lower number, which is equal to the natural log of the higher number divided by the natural log of the lower number, or the common log, or log base 17 of A over log base 17 of B. All of these ratios are the same. So when you had log base 2 of 3, was that the problem?
2 of 7.
Log base 2 of 7?
Yeah.
That is the, well, she said change it into natural logs, right?
Yeah.
The way I memorize that is it's the log of the big number divided by the log of the little number.
Yeah.
And it doesn't matter what kind of log you use. And that's what you need. What kind of calculator do you have? The TI-84 or the Inspire? You have the 84, don't you?
I have the 83.
The 83, okay, same thing. You only have a natural log key and a common log key on that thing.
Yeah.
So if they were to give you this problem, you would only be able to solve it using the change of base formula.
Yeah.
Because you don't have a log base 2 key. So actually the change of base formula is a pretty good one to remember, since your calculator doesn't do bases other than natural log, which is base E. E is equal to approximately 2.71, but it's an irrational number that goes on forever. That's what natural log is it's log base E. E is one of those extremely special numbers, right up there with pi. E and pi might be the two most important numbers in math.
Yeah, my teacher said it's like, it's with pi and square root of 2 and I.
Yeah, they're irrational. All of those you just named are irrational. You cannot write them as a fraction. You can approximate them as a fraction, but you can't write them as a fraction.
Yeah.
Okay, what else you got?
Here, evaluate each and it's a natural log of 1 divided by square root of e to the 7th.
Like that?
Oh, it's a natural log of parenthesis 1 divided by square root of e to the 7th.
Okay.
So, or quantity.
Like that?
Yeah. Yeah.
Okay. Well, what's another way to write this? First of all, let's remove the radical sign for beginning, for starters.
That would be e to the 7/2.
Okay. Now let's remove the denominator. In other words, let's put it in the numerator. How do you do that? 1 over x would be x to the minus 1. 1 over x squared would be x to the minus 2.
So we would make everything times negative.
Not negative. A negative exponent, which does not have anything to do with negative numbers.
Yeah.
Negative exponent merely means reciprocal. Okay? But now, because we have a exponent instead of a radical sign, we can do something with it. What can I do with that exponent? Based on rule number 3.
Doesn't natural log and e cancel, and then it's just 7/2?
Yeah, but it starts with taking this exponent and bringing it down onto the algebra line. So it becomes minus 7/2 times the natural log of e, and that is 1. So the answer is minus 7/2. And you could say that the natural log of e to any exponent is equal to the exponent, but it's because of this. It's because rule number 3, remember, look at rule number 3, Rule number 3 lets you take the exponent and put it down as a multiplier of the log function.
Yeah.
And that's what we've done here. All right. In fact, let's go over another rule for logs. The log base b of b to the x is equal to x. And that's what we just had, notice. We had the natural log of e, and natural log is base e, to the minus 7/2 was equal to minus 7/2.
Yeah.
Because of this. And that's true regardless of the base. In other words, if I said, what is the log base 17 of 17 to the x squared plus 1, what's that equal to?
It's x squared plus 1.
Yep. Okay, what else?
The next one says
Before we go to that one, let me just quiz you on something. Tell me what that is the exponential expression of that equation. What is the logarithmic expression of that equation?
that would be log base 2 of 8 equals 3.
You want to be able to go back and forth between these things. They're both equal.
Yeah.
And it's a good skill. Make sure you can go back and forth. It appears you can. In other words, you want to be able to go from this, which I think of as the number on the far left raised to the power of the number on the far right equals the number in the middle, or the other way, where you have an exponential expression and you need to convert it to logs. That's a key. That's a key ability. Okay, what was the next one you were going to throw at me?
This one, it says solve, and it's 3 minus log of x plus 2 equals 5.
5?
Yeah.
Okay. What do I need to do here?
Well, first thing I would do is subtract 3.
Okay, we can do that. Usually when I'm looking at a problem like this, I'm going to try to get the coefficient positive as quickly as possible. And I could do that if I move this whole thing to the other side. And I move the 5 to the left. You're going to get there. You're going to get to the same thing. You're going to get there. And now you have to divide both sides by -1. Now what? And the solution to this always lies when you get to this very final step where you have the log of an expression equals to a number. The solution always lies in converting it to the exponential expression. So convert that to an exponential expression.
So it would be log.
No, that's a logarithmic expression.
Oh, no, 10 to the minus 2 equals x plus 2.
Good. And see, now we can solve for x. Now we have an algebraic equation. Algebraic equations, we can always solve for x.
So 10 to the -2 is 0.01.
Uh-huh.
So, or 1/100th is, yeah.
So x is going to be minus 1.99. What is this equal to?
That would be equal, that would be 0.
Yeah, always, no matter what the base is.
Yeah.
Log of 1 is 0. What's this?
Isn't that like, doesn't that not work? Or
Yeah, notice that if I were to do this and then convert it to exponential, I would say 10 to the x equals 0. Well, there is no x that would make 10 to the x equal to 0.
yeah.
Not negative a million, not 0.01 or anything. You can't
So
get
that
it equal to 0. Therefore, you cannot take the log of 0. That is outside its domain. In other words, this is a little interesting. Domain of that function is x greater than or equal to 0, right?
Yeah.
Domain of this function,
Is anything but 0?
no, has to be greater than 0. Can't be negative, can't be 0.
Oh, that's true because,
So
yeah.
the log function is more restrictive than the square root function. You can take the square root of 0. You can't take the square root of negative numbers, but you can take the square root of 0, but you can't even take the log of 0.
Yeah, and then you can't do log base 1 either.
Right. Yeah, there ends up not being a whole heck of a lot of use for logs of any base other than e. Log base e is such a huge part of all higher mathematics that you kind of forget about all other logs. And once you get to calculus, everything is ln. And you don't really, I mean, you can handle log base 2, but not sure who uses it. Perhaps at some other higher level of maths, you end up in those odd bases.
Yeah.
But natural log is such a, E is such a vital part of so many different real-life processes, from population growth to radioactive decay to bacterial growth. It all comes down to this number E, believe it or not. And
Yeah.
that's why natural log is so huge in mathematics. What else you got?
Here. Use use properties of logs to rewrite each as a sum or difference of logs.
Okay, sounds like we're going to expand here.
Yeah.
Okay.
And it's log x y to the third.
All of it?
But no parentheses. It's just y.
Okay. What's that going to be?
It's gonna be
Do it one step at a time. I think the secret on these is don't try to do the whole thing at once. In other words, use the product first. The fact that we're multiplying inside the argument means we can separate it with a plus sign. So let's do that part first.
So it's log x plus log y to the third.
Yeah. Now you can use rule 3 to bring the 3 down in front. So the full expansion would be this. And that's the way to do it, I think, is one rule at a time. Don't try to do them all at once. Unless maybe you have division going on, and then you know, if it was all divided by z, well, then I would know there's one more term coming, minus log of z.
Yeah.
So this would be your answer. Now, we don't have much time left. Do you have any log equations? Have you gotten to log equations yet?
I think we touched on them, but they're not going to be like on this test.
Okay. If they were, I would want to go over this.
Oh, well, here's one that we could do as like the last one.
Okay, go ahead.
1.05 to the x equals 3.
Okay.
So
Solve this by using the properties. Well, notice we don't have an algebraic solution to this.
yeah.
You can't really go into your calculator and say 1.05 to some power equals 3. It's not going to tell you that power. This is why we have logs, though, because we can take the log of both sides of an equation. And I like to use natural log here. Doesn't matter which, but like I said, natural log is the function of choice. So I'm going to take the natural log of the left side and the natural log of the right side.
Yeah.
In other words, you can do that. You can do anything you want to either side of the equation as long as you do it to both. Now use Rule 3 to simplify the left side. Bring the exponent down to there.
Yeah. So it would be x to the natural
x times natural log of 1.05.
Yeah.
That's what the left side is equal to. Now notice that is a number, so is that. So what's the next step?
It's divide natural log of 3 by natural log of 1.05.
Now, is there anything we can do to that function to simplify it?
Yeah, we can find the natural log of 3.
Right. Yeah, but what I was getting at is we cannot use the rules of logs on this. And a lot of people will confuse that. In other words, they'll see two logs being divided. Can I make that the natural log of 3 minus 1.05? And the answer is no, you cannot. In other words, if it was natural log of 3 divided by 105 like that, then that would be equal to the natural log of 3 minus the natural log of 1.05. But I have nothing that lets me simplify that expression. I have to, as you said, go into my calculator, come up with a number for that, and go onto my calculator, come up for a number for that, and divide them.
Yeah.
Okay. All right. If you're not going to have log equations, that should about cover it.
Yeah.
Let me just say one thing about log equations real quick. If I had this, the way you solve this equation is by using the properties to combine, so you end up with this, right?
Yeah.
Then you convert it to exponential, so it's 10 squared equals x squared plus x. 10 squared is 100. Okay?
Yeah.
Then you solve that quadratic. That quadratic, in other words, if I subtract 100 from both sides, I get this. Now, I've got two solutions that are going to come out of that. I picked these numbers out of thin air, so I didn't make a real easy one. But you can always use the quadratic formula, but the fact of the matter is that one's going to be positive, one's going to be negative.
Yeah.
You have to throw the negative one out because it violates that domain right there. And you always have to check the original function for domain violations. You can't check this one.
Yeah.
In other words, if I had this problem and it turned into just x squared, now notice that if I take my positive and negative solution, it does not violate this, but the negative would violate the original. You cannot check the domain restrictions on anything but the original function. You always have to go there. And almost always, one of the solutions violates the domain, so you have to throw it out.
Yeah, we like with the polynomial equations that were like division or simplifying stuff, I just, to like make it easier, I came up with the rule always go back to the original.
Yes.
So like the most domain and range.
It's a little confusing as to why the second is not exactly the same as the first, but that's the truth of it, is that you have to go back to the original.
Yeah.
All right, Lucas.
Okay.
Good luck on your little quiz, and probably next week we'll be working on those log equations, is my guess.
Yeah, probably.
Yeah, okay. Talk to you then.
All right, bye.
Bye-bye.